one more example about checking the thermal efficiency and everything for a power cycle in this problem. So here we've got a power cycle. It receives 1000 BTU by heat transfer from a reservoir at 1000 degrees Fahrenheit, and it's going to discharge energy by heat transfer to a reservoir at 300 degrees Fahrenheit. The thermal efficiency of our cycle is 75% of that for a reversible power cycle operating between those same reservoirs. Now we got two things to do here. Part A, for the actual cycle, we want to determine the thermal efficiency and the energy discharged to the cold reservoir. Units need to be in BTU. Part B, we're going to repeat that for the reversible power cycle. So to get started, let's draw out what the system looks like. We got the hot reservoir up here. The temperature is given as 1000 degrees Fahrenheit. Now we don't ever do anything with Fahrenheit or Celsius, really. We always convert over. So I'm going to go ahead and convert this over to Rankine. Rankine is an absolute temperature scale, so we can use degrees Rankine. So it's 1460 in Rankine. Now we got this little box, represents our system. Here we got cold. This will be the cold reservoir. This temperature was given as 300 degrees Fahrenheit. Again, let's switch that over to Rankine. So that'll be 760 degrees Rankine. Now remember, this is a power cycle, so we've got energy transferred by heat coming from the hot reservoir. That's our QH. And then generating work here. That's QH minus QC. And then for the cold reservoir here, we've got QC. So we're discharging energy by heat into that cold reservoir. That amount will be QC. All right, now we also have that the power cycle receives 1000 BTU by heat transfer from the reservoir at 1000 degrees. That's telling us what QH is. Right, so QH, so highlight that there. QH is 1000 BTU. So we were given that. And we are also given the fact that the thermal efficiency of our cycle is 75% of that for the reversible cycle. Now if we write that out in equation form, that means eta is going to be 0.75 times eta max. Now remember why that is? That's because this eta max was for a reversible power cycle. Okay. So now that takes care of this information that was given to us in the problem. So that's good. Now let's go ahead and find eta max. Let's look at our equation for that. Remember that max equation is going to be 1 minus Tc over Th, because we replace our Q values with the temperatures for the reversible process. Now we can plug in our temperatures. Tc for this one is going to be 760. So we'll have 1 minus 760 degrees Rankine, and then Th is 1460 degrees Rankine. So temperatures go away. This is going to give us 0.48. So this is not very efficient. We only got 48% here. And the actual cycle we have is 75% of this. So eta is going to be 0.75 times 0.48. It gives us 0.36, or 36% efficiency. Okay. So that's what we get for our thermal efficiency. Now we also need to find the energy discharge to the cold reservoir. That's going to be this QC. We need to find QC now. We know that the work of the cycle is QH minus QC. So we can solve that for QC, because that's what we're looking for. So we'll have QH minus the work of the cycle. And now let's figure out what to do with that, because we don't know what the work of the cycle is yet, do we? Nope, we don't know that. Now let's look at our equation for eta, our thermal efficiency. If you remember, that had work of the cycle in it. And the equation was work over QH. That means we can solve this equation for this work, and that's what we need up here. So work is going to be our efficiency times QH. We already have our efficiency. We just found it up here, right? QH was a given. So we're on our way. Now let's replace this in our equation up here. So we can put QC equals QH minus eta QH. And then let's plug in our numbers. We'll have QC. Notice you have QH here. I'm going to pull that out. QH is 1,000. This is BTU. Multiply that by 1 minus 0.36. That gives you a QC of 640 BTU. There we go. That gives you our energy discharge to the cold reservoir. Now, if you think about it, this is a lot of energy just to be discharging to the cold reservoir. Under ideal circumstances, you would want to convert this over to work. All right, but we don't have a very efficient process, so we're discharging a lot of that energy. Now, for part B, we want to repeat this for the reversible power cycle. So for B, we want the reversible, so let's spell that out. Now we already know that that efficiency is going to be the max. We already found the max efficiency, right? So 0.48. That's not going to change because we're not changing our reservoirs. We're keeping those same reservoirs. We're just assuming a reversible cycle. So the max here would be 0.48. That would be what you'd get if you had a reversible cycle. And then QC, you're just going to use the same equation here. QH isn't going to change, so you're still going to have the 1,000 BTU times 1 minus 0.48, which gives you 520 BTU. That's your QC. All right, we finished that one. Perfect. Now the key thing to notice on here, students typically don't have too many problems with this section because the equations are pretty straightforward. You just have to remember that your max here is for a reversible cycle. Reversible is the best you're going to get. So if it asks you for, like it did here, it wants the efficiency for a reversible cycle, you know that that's got to be your max calculation. All right. I will see you guys next time.